Hello again. In Newtonian mechanics, there are certain quantities that are very important, and that are very important that we define concisely and precisely. And in another tape, when we spoke about Newton's laws of motion, we derived a formal definition of force. And just to refresh our memories, in that instance, force is equal to the mass of an object times the acceleration of the object. And this has units of kilograms, and acceleration is a measure of change of speed with time. And so this has units of velocity with respect to time, or meters per second squared. And so the units of force are essentially kilograms, meters per second squared. And because we like to have shortcuts and we like to honor scientists who come up with these ideas, this system of fundamental units here has a name, namely the Newton, and it is abbreviated as a capital N. If you spell it out, it is spelled out in all lowercase letters. And so that is our formal definition of force, and it derives from Newton's second law of motion, as we said. Now, one of the things that objects in motion do is that they are capable of doing work. And again, work has a very, very precise definition to it, and let's just lay out what that definition of work is. Let's abbreviate work as W. If you take an object and you exert a force on it, here's our force, and you move it from point A to point B, you've moved that object a certain distance. And when you exert a force on an object and you move it over a distance, you have done work on that object. And so the formal definition of work is the force exerted on an object over some kind of a distance that we define. And obviously this has the same units as force, but now we have the additional unit of distance. So kilograms, meters per second squared. That's our definition of force. And of course, distance has units of meters, and the product of those has units of kilograms, meters squared per second squared. And there's a special name that goes with that as well. The unit of work is known as the joule. And the joule is named after the British scientist that did pioneering work in the study of work. When we write it out as an abbreviation, it's a capital J, and if you write the unit out fully, it is all spelled in lowercase letters as the joule. All right, the final unit that we need to develop formally is the unit of power. And power is simply a rate at which work is done. And so if you have an object being acted upon by a force, moving it over a distance d, power is a measure of how quickly you do this. If you do this transformation quickly, then you have generated more power. You've expended more power to be able to do it. If you do it more slowly, then the power requirement is less. And so power is basically a work rate. And so we can define power as essentially work divided by time. And now we have our units of work, kilograms, meters squared per second squared. But now we divide that by time. And what we end up with is units that have these properties: kilograms meters squared per second. Okay, and that is a measure of power. And so, just to reiterate, we have three basic concepts that govern Newtonian mechanics. One is the concept of force, which is equal to mass times acceleration. That derives from Newton's first law. Work is force acting over a distance. That was formulated about a century after Newton did his original work. And power is simply a measure of work rate. Force has units of newtons. Work has units of joules. 1 joule is 1 newton acting over 1 meter. And power, oh, I didn't put in the units for that. The power is given the name of watts. And when you spell that out, you use it in lowercase letters, but if you abbreviate it in a paper, it's a capital W. Okay, so, and power is a work rate, and it is essentially 1 joule per second is equal to 1 watt. Okay, that's all for now, and we'll see you next time.